Hello, it's Bill again, and today I want to give you an entropy update. This is a previous video that I did, but I had to update it after I found some errors and also wanted to add some other things as well. So without further ado, now what we discovered is it appears to be a new second law of universal law of entropy. In local systems, entropy increases or remains constant in idealized processes, but on a universal scale, entropy is conserved through the redistribution of degrees of freedom between cosmic and local scales. And basically what we see is a change in entropy cosmic plus a change in entropy local equals zero. And there are three cases in which entropy conserves. Case one. A local particle crosses a cosmic event horizon and leaves one bit of negative energy at the cosmic Landauer limit, adding one Planck area to the cosmic horizon. So here we can say or see that there's a particle and it crossed the cosmic horizon, so it's no longer causally attainable, so -1 s local. But then the cosmic horizon expanded one Planck area. Case two. Cosmic horizon uses one gravity bit to resolve entangled matter pair spin uncertainty, erasing one Planck area on the cosmic horizon, offset by adding 1 unit of Hawking radiation locally, conserving total energy of the universe. So entangled pairs, after they're entangled and A is measured, A erases 1 bit of its cosmic horizon, which resolves B locally. And then when B is measured, it emits a Hawking photon. So -1 s cosmic for the cosmic horizon getting smaller, +1 s local for the Hawking photon. So here we have a case of the host particle, host space, host horizon, and guest particles. And we're going to show how these things interact. So this is going to be the host space. This is the host particle, and this is the guest particle that crossed. And this is the host particle's cosmic horizon. And rather than thinking in Cartesian coordinate systems, it's probably more useful to think in terms of polar, because this particle will have its horizon this direction, all directions, because the cosmic horizon is a sphere. And once the red particle crosses the boundary of the green host here, it is encoded as 1 extra Planck area. Now here's the reverse. We showed that what happens when we had a green host particle and a red guest. Well, in this case, we're going to look at the red particle. And we're looking at the red particle's perspective as it's a host. At the very same time green crossed red, the same time red crossed green's cosmic horizon, green also crossed red's. And you can see they're at the same location, but green's cosmic horizon was here when red crossed. But on red's perspective, it's green that crosses red's cosmic horizon. Red's cosmic horizon appears to gravitate green out of the red host's observable universe. And this means that once one of the particles crosses, it's symmetric. Both red and green each have 1 Planck area added to their cosmic horizon. So this is how the red-shifted energy from particle crossings turns into Planck area. The guest particles that crossed the host horizon had their guest spin red-shifted energy encoded on the horizon as negative energy holographic Planck tiles. We're going to introduce a new formula here. E observable equals E initial divided by 1 plus Z. And Z is the redshift. E observable is the observed spin energy value of a distant particle, also known as the guest particle, and includes all Doppler shifted energy values. E initial is the energy of the guest particle expressed when local to the host particle. This value is the spin energy determined by the Landauer limit at local curvature. Z is the amount of redshift, which is infinite at the cosmic horizon relative to its host particle. So when Z is infinity, when redshift is infinity, then E observable equals 0. We'll set E initial to 1 for 1 quantum unit, and this sets the reference for the energy exchange, which is 0 minus 1 equals minus 0. This bit of negative energy is only relative to the host particle and its host horizon. And this is how gravity is derived from negative energy. Now here's the third case of entropy. Horizon expansion from the Big Bang encoding other host particles as guest particles on a host particle's cosmic horizon. So in this case, we have a Big Bang. We got an orange particle way over here. In the Big Bang, all cosmic horizons expanded as all the Hawking photons were condensed. And this cosmic horizon expanded. Now blue was out of causal contact. It crossed orange's horizon a long time ago. But now that the Big Bang's happening, orange's cosmic horizon starts sweeping outwards. And as it sweeps across this blue particle here, orange's horizon encodes blue's information as guest spin. And now we have guest blue in orange's universe. And this is how the entropy worked for the Big Bang. At the same time that orange's cosmic horizon encoded blue, blue's cosmic horizon expanded and encoded orange. So in blue's universe, orange is actually a guest particle projected from the guest spin. In orange's universe, its version of blue is a guest version of blue, and its guest spin is encoded on orange's horizon. And this is how the 720 spin works. This is the orange host's first rotation of 720 spins, so 360 degrees here. But then blue's impression of orange is the guest spin, and that's the second rotation, offset by temporally by the light delay between the two particles. So every particle has their own cosmic horizon, which contains holographic information about all other guest particles which have crossed the host particle's horizon. All guests in that host observable universe and Hawking information. This means each host particle includes a universe worth of information on the cosmic horizon. Guest particles are hosts in their own observable universes. The host is simply the first rotation of 720 degrees of quantum spin. Each host has 10 to the 122 guest expressions, one each in every other observable universe, so the second rotation of 720 spin is distributed across every cosmic horizon that is not the host's own horizon. This is what makes matter matter, the mutual encoding of every 720 spin particle with every other. So we're at the large young universe phase. Big Bang had created 10 to the 122 particles, which became structured and encoded all of the particles in our universe. So we have 10 to the 122 Planck areas on the cosmic horizon, giving us all of this wonderful space from the 10 to the 122 particles that crossed. Now we have 10 to the 80 guest particles, all the other information, stars, planets, people, everything else in your observable universe. And there's also a few Hawking photons, which are receipts for erased Planck areas. But not much gravity has been made over 13 billion years. We have 10 to the 134 years of gravity being made before the universe becomes so small it resets. So the late small universe, most relative gravity bits have been emitted, shrinking the cosmic horizon to possibly as small as 2 times 10 to the negative 18 meters, which is the size of a neutrino. 10 to the 18 Planck areas on the cosmic horizon of an object that small. Few guest particles due to high dark energy. Because this horizon is so small that, remember, this acts like a black hole surface, so any other particle in this tiny universe is going to be immediately ripped across the small horizon. So there are as many Hawking photons in this era as there were Planck areas of the cosmic horizon in the large young universe. So each time gravity was emitted, this large universe got a little bit smaller and smaller and smaller until now it's very, very small. And now each one of these erased Planck areas from this era actually contain with Hawking photons inside this envelope. So now we have enough information, we can calculate the total size of the universe because each particle is related to every other particle. Every host is at the center of their own universe. So we have 10 to the 122 negative energy bits on each host horizon, giving us a radius of about 13.8 billion light years for each observable universe, each bit representing a particle that crossed a host horizon. The uncertainty from those particles crossing a cosmic event horizon projects that energy of uncertainty as space-time. All cosmic horizon entropy responses are irreversible, meaning if you erase a Planck area to resolve entangled pair AB, you cannot re-entangle AB to put a Planck tile back on the cosmic horizon. Once a particle crosses and adds a Planck area of a cosmic horizon, that particle can't be retrieved. And the particle re-encoded, the Planck tile addition is subtracted. That cross particle is out of causality until the next Big Bang. Now this means that there's 10 to the 80 guest particles in each observable universe, so there are 10 to the 42 observable universes that are out of causal contact with each other. We have a total of about 10 to the 24 stars in each observable universe, so there's going to be 10 to the 66 unique stars in all observable universes in this entire 3D hyperspace sphere structure. Thank you for joining us on How Entropy Conserves, and be sure to watch my YouTube channel, Gravity for the Masses, and watch the playlist. I got a lot of good information on the playlist. Have a great day.